Hi guys, Gibson here. Today we're going to take a look at our first lesson in this unit on light, and we're going to talk about the fundamentals of light and color. How do we produce colors and how do we perceive it? So let's take a look at our objectives. So the first thing we're going to do is take a look at the two different models of light, and these models are used to predict or explain certain behaviors of light. The next thing will be to understand that light is an electromagnetic wave. So we've been studying waves in terms of physical waves, sound waves, vibrations, and strings and solid material. So how is an electromagnetic wave similar and different? And then we'll look at what is the full spectrum of wavelength and frequency for electromagnetic waves, and where does color fit into that? Then we'll see, does the wave equation still apply when we're talking about light waves or things moving at the speed of light? And then we'll get into color. We'll first look at what we call color addition. How do we produce colors by combining light? And then the second way we produce colors is by a process called color subtraction. And this is where we use pigments to absorb or subtract color and create different colors of materials when light shines on it. So the first concepts of light were interesting. This goes back a couple thousand years. Some of the early Greek philosophers had some ideas about this. Some of them thought that light consisted of tiny particles which entered the eye. So for example, if they were looking at an apple, there were little tiny bits or specks of those apples that would travel into their eye, and that's how the human brain would perceive that, oh, that's a red apple with a certain shape. Others looked at it a little differently, that there was some type of streamer or filament that came out of your eye to the object and then somehow transmitted that information back to the brain. So the streamer would go out, touch the red apple, and then somehow convey that information back for us to process. So one was the thought of a particle of some sort, and the other was some type of streamer, or if you look at the way I've drawn the model here, it really looks like a wave. Well, it turns out they were both right, at least at a very conceptual level. Light behaves as both a wave and a particle. The wave theory was first published by a physicist named Christian Huygens way back in 1690, where he proposed this theory that light is a wave, and then was able to use that principle to explain a lot of different behaviors of light if we model it as a wave. I mentioned the other model we use is a particle. So the concept of light as a particle from a scientific standpoint came more recently. Albert Einstein published what we call the photoelectric effect in 1905 and came up with this term of a photon. So a photon, think of it as an individual little packet of light or light energy that can create certain behaviors as it travels. So as we get more into the unit of light, right, we'll be looking at both of these models. But for now, what I want to share with you is that we could use either of these models to explain some of these behaviors that we'll be studying as we move through this unit. So reflection, refraction, diffraction, these are all behaviors of light where light changes its direction. And so if we look at reflection, that can best be explained by the wave model. Same thing with refraction. Interference, it's the same concept that we studied in sound waves, how they can have constructive or destructive interference. So the wave model helps us explain that. Diffraction is the spreading of light as it goes around a opening or a edge of something. Wave theory helps explain that to us. Same thing with polarization. The photoelectric effect is the one behavior that clearly can only be explained using the particle model. Now, recently, some physicists have said, well, we can use the particle model to also explain reflection, and refraction. But the classic approach is to use the wave model to explain that. Now, I'm not going to go in detail of what these different behaviors are of light. This is things for a future lesson that we'll cover as we go through this unit. All right. The key concept is that light is what we call an electromagnetic wave. An electromagnetic wave is created by emitted by electrons that are accelerating, okay? So if you have an electrical charge, and typically that would be an electron in an atom that's moving back and forth, right? Either changing its speed or direction, which electrons tend to do most of the time, that acceleration emits energy in the form of an electromagnetic wave. So let's take the example of a good old-fashioned light bulb. It has a tungsten heating element, right? If we, let me put my highlighter on here. If we look closely at a light bulb, right, this little tiny wire inside here is a piece of tungsten. It's a unique metal that has some properties. And what happens is when that tungsten is heated up by passing an electric current through it, it causes the electrons in that tungsten to accelerate at a certain rate or frequency that produces visible light or useful light. So that light is emitted, or that energy is emitted as an electromagnetic wave. So light travels in a wave that is really has two components to it. It has an electric and a magnetic component, hence the name electromagnetic wave. So the electric wave is produced in the vertical plane if we think of the electron as oscillating up and down in the vertical plane. So basically within the screen here, going up and down. So that gives us an electric wave. The magnetic wave gets produced at a right angle to that. So that would be in and out of the screen. So you have to think in 3 dimensions here for an electromagnetic wave. Okay, so here's a little picture that helps us to see that, right? The red part is the electric wave. Let's get my laser pointer on here. The red part is the electrical wave, and the blue part is the electromagnetic wave. So if you can think about it, they're going at right angles to each other as they oscillate up and down and in and out, okay? The direction that the wave energy propagates, in this example of the drawing, would be left to right here on your screen. What's actually varying is the electric field strength or the magnetic field strength. Now, we haven't studied electric fields or magnetic fields. Hopefully we'll get to those a little bit before the end of the year here. But that's what's actually varying in terms of the amplitude here. It's the strength or intensity of the electric field and magnetic fields. So here's a little animation that helps us to see this a little bit and compares it to a mechanical wave. So the top wave would be like if we had a string, right, that we're vibrating up and down. And you can see this would be in the vertical direction, but a mechanical wave could really be in any orientation here. This particular mechanical wave, right, would be a transverse wave, but mechanical waves can be either transverse or longitudinal, like the Slinky lab we did had both examples in it, okay? The key with a mechanical wave is that it requires some type of medium to travel through. So either a gas or liquid or solid, or I guess you could throw a plasma in there as well. But one of those states has to be present in terms of a medium because it's the actual atoms or particles in that medium that are vibrating, that are moving up and down, or if it's transverse or moving parallel, if it's longitudinal. The electromagnetic wave, as I mentioned earlier, it's a variation in the electric and magnetic field strengths. Okay, so that's what we're seeing with the red and blue animation down below. But the key thing with light waves or electromagnetic waves is that no medium is required in order for it to travel or be transmitted. Okay? So think about it, we know by experience, right, that light can travel through the vacuum of space. How else would the light from the stars and the moon and the sun reach us, right? It has to travel through a vacuum. So the key thing about electromagnetic wave is that it doesn't require a medium to travel through. Now, does light travel through air? Certainly, right? It travels through our atmosphere. Does it travel through liquids? Yes, we can see light through a glass of water. okay? And as we get further in, we'll see, well, what happens to light when it travels through different mediums, okay? But light doesn't require a medium. It can travel through the vacuum of space because it's simply the electric and magnetic fields which can form without any medium. All right, so let's talk a little bit more about what is it that allows light to travel through some objects like water or glass and not through other materials like wood or stone. And it has to do with resonance, okay? But here's the two requirements. It depends on the frequency of the light that is hitting the object or media and the natural or resonant frequency of the material. And this is typically the natural or resonant frequency of the atomic structure in those materials, so the electrons. So let's look at a very kind of simple model of an electron here. We have our nucleus and we have our atoms that are vibrating around it. Now, if a light wave hits that atom, it's going to impart energy from that wave, and the energy will be absorbed by the electrons, and the electrons will do one of two things, right? If the frequency of the light matches the natural frequency of the atomic structure, then it will absorb that energy and retransmit it as heat. Okay, so in this case, it'll absorb the light, it'll produce heat, but it won't retransmit the light, either reflecting it or passing it through. Okay. The other case is if the light does not excite the atomic structure at its resonant frequency, then the light gets passed through that atomic structure. Okay, so this is what would happen if we had transparent materials when light shines through it. So let's look at these two cases a little more here. So first off, if we have a material that does not transmit light, but permits sometimes some reflection of light, we call that opaque. Okay, so that's the key word here, is opaque material. Let me put my highlighter on. So opaque materials are things that will not allow the light to transmit through. Some materials can be opaque, but actually reflect it. But the key is that the light frequency matches the resonant frequency of the medium. So a block of wood, for example, right? Any vibration of the atoms or molecules that's caused by the energy of the light is just turned into random kinetic energy, right? So if you take an object, think about the ultimate object that will absorb light is like a black object, right? If you set a black object out in the sun in the day, what happens to it? It gets warm, right? Why is it getting warm? Because it's absorbing the energy from the light and changing that energy into a heat form, okay? Some materials, such as our metals, can reflect a large amount of the incident light, okay? So they may absorb some of it and then they reflect the rest of it. So clearly metals like gold and silver, anything that has a very smooth, shiny surface to it has the ability to reflect most of the light. The other case is transparent. Okay, so that's the key word here, transparent. And this is when the light does not match the resonant frequency of the medium. So what happens? Let's look at our model here. So let's say we have an atomic structure of, say, glass, and we have these chain of molecules, right, that are what creates the glass. So the light ray comes in, it hits that first molecule. The molecule is going to vibrate a little bit with that energy, but since it doesn't match its resonant frequency, it's not going to vibrate in a large way and produce much heat. What it's going to do is retransmit that energy through the molecular structure and then eventually re-emit the light. Okay, so it's kind of this chain reaction that happens as light passes through a medium like glass that is transparent. It has to kind of go from molecule to molecule and have this type of reaction, but ultimately it will retransmit that light as it reaches the other side of the material. Okay. So if, for example, window glass that we use, right, is transparent to all visible frequencies of light, what we would normally perceive with the human eye. And that's what makes it so great, right? It lets all the different color spectrums into our house so we can see clearly what it looks like outside without any filtering of colors. Um, Now, one thing glass doesn't transmit is electromagnetic waves that are in the ultraviolet range. And we'll talk about the spectrum here in just a minute, but I'm sure most of you are familiar with ultraviolet radiation or waves, right? It's still an electromagnetic wave. It's just like light, except we can't see it. It's a little bit higher in frequency than the visible light spectrum. Ultraviolet has a bad reputation, right? This is what can cause a sunburn or a skin cancer if we have too much exposure to it. But glass actually likes to vibrate at the natural frequency of ultraviolet electromagnetic waves. So what's it going to do if it matches? It's going to absorb that energy from the ultraviolet rays. So glass is a good material because it filters out the ultraviolet rays but allows the visible light spectrum to come through, right? So that's why if we're driving in a car and the window's up, right, we're kind of protected from the ultraviolet rays. If we roll the window down, put our arm out the window and drive for hours, we're going to get a nice sunburn on our arm. So we would say glass is opaque for ultraviolet rays, but transparent for visible light, okay? All right, the last case we can have is something called translucent. So translucent means that light can transmit through, but it doesn't allow objects to be seen clearly through them. So really what's happening here is some of the light is absorbed, doesn't get transmitted quite as strong, and as it does pass through, it gets scattered. So it kind of makes the image much less clear. So here's some examples, right? Sometimes in our bathrooms, for example, we have glass in the windows that is translucent. It allows light to come through, but you can't see a clear image, right, for privacy reasons. A water wave in the ocean, if you see it breaking, right, you can see light coming through it, but couldn't see images really clear. A piece of quartz, similar thing. And some animals, like this little cuttlefish here, or squid, their bodies are made up of translucent materials, right? They actually, some of them are bioluminescent. They can create a light source from inside, and you can see it kind of shining through their translucent bodies. Okay, so the three behaviors we get in terms of light hitting an object is either opaque, right? It absorbs or reflects. Translucent allows the light to pass through with very little loss and with good clarity. And then translucent, I'm sorry, I should have said transparent, right? Translucent is when we get some light through, but it scatters so we don't get a clear image of what is attempting to come through. All right, speed of light. This is something most people know is very fast. Sometimes it's referred to as the speed or speed limit of the universe, right? We have this principle in physics that nothing can travel faster than the speed of light. Well, exactly how fast is the speed of light? Well, it's pretty difficult to measure. Why is that, right? Well, could we do this, right? Could we think of a practical method to measure the speed of light? In other words, if I stood at one end of the classroom with a flashlight and you at the other end with a stopwatch, and when I said go, I hit the button, and as soon as you saw the light, you stopped the flashlight, right? Or stopped the stopwatch, rather. So would that be a very effective method? Well, I think we can all agree that no, because the light will appear to be instantaneous, right? Because we know it travels very fast, but it travels such a short distance, there's no way we could measure that time interval. So how do we come up with the speed of light? How did we first measure it? Well, there was an American physicist named Albert Michelson back in the late 19th century that worked on this problem. And here's the setup that he did. He started out with a mirror that rotated, and on the sides of the mirror, get my pointer back here, on the sides of the mirror here, or the wheel here, was a mirror. So it had 8 sides to it, and those sides were kind of covered with a mirror. He had a light source. Now I'm showing a laser pen, right? He didn't have a laser pen back in the 1880s, but they had basically gas lights with lenses that could focus it into a beam. And then he took a mirror and placed it on a mountaintop quite a ways away. And then it turned out about 35 kilometers away. And then he had a detector, right, that would see when does that light beam reflect off the mountain and come back, hit the mirror, and hit the detector. So the light would take this path, right? It would bounce off of one of the sides of the mirror, hit the mountain, come back, hit the mirror again, and then go to the detector. So the thing is that when he did this experiment, he had the mirror spinning. And that's a key factor here, because actually, I take that back. There was only one side of the mirror that, or the wheel that had a mirror on it. So as he spun it around, he had to make sure that he had just the right speed so that when the light first reflected off that one side of the mirror and it came back from the mountain, it would hit that same side of the mirror, but just slightly turned, right? So he could adjust the speed for that. So here's what it would look like, right? If I can do this right with my keyboard here. So he hits the light and it comes back from the mountain and reflects off of that. So he knew what the round trip was, right? 35 kilometers. He adjusted the speed of this mirror and it turned out to be about 32,000 revolutions per minute, so pretty fast, in order to get the reflected light to catch just the right surface of the wheel and send it to the detector. So the time for 1/8 of a rotation, you could see, was very small, a fraction of a second. So if we did the math, right, 70 kilometers distance divided by time gave him the speed of light. And he came up with this number, 299,920 kilometers per second, okay? So remember, this was, gosh, almost 120 years ago when he did this, okay? And guess what? That number was very close to what we use today. So for that, Albert got a Nobel Prize in physics. So let's officially define the speed of light. Here's the value. You can see that it's very close to what Michelson had, 299,792, 458 meters per second. Now, on the problems that we're going to use the speed of light in, we're not going to try and remember or use all these digits. We're going to round it off to this number right here, which is basically 3, and we'll keep it in scientific notation, 3 times 10 to the 8th meters per second, okay? So that's about 300 million meters per second in terms of the speed of light, very fast. The symbol we use for the speed of light is a small c. So I'm sure have heard the concept of a light year, right? It's a distance measurement that's used in astronomy. How far does light travel in 1 year? So let's actually calculate that, right? If we start with this speed, 3 times 10 to the 8th meters in 1 second, we want to basically say, well, then how far would it travel in a year? So let's multiply seconds until we get up to a year. So first we know is there's 3,600 seconds in an hour, so we'll multiply by 3,600, 24 hours in a day, so we multiply by 24, and then to get to a year, we multiply by 365. So if we grab a calculator and do all that, we get this really big number, right? Well, first let's do the unit analysis, right? Seconds cancel, hours cancel, days cancel. So now we're left with meters, right, per year, which is what we're trying to find here for a light year. So we get this number, 9.46 times 10 to the 15th meters per year. Huge number, right? Kind of hard for us to relate to that. If we convert that into miles, it would be about 6 trillion miles, right? So you got millions and billions and then trillions, okay? So huge amount of distance that light travels in 1 year. Now, in terms of us being able to travel to other solar systems, guess what? The nearest is Proxima Centauri. It's about 4 light years away, or 24 trillion miles away. Okay, so even if we could travel at very nearly the speed of light, it would take us 4 years to get there. And before we finish up this unit on light, we will talk a little bit about what happens when you travel near the speed of light. And you can see that is a very difficult thing to do, even to go a small percentage of the speed of light, because of what happens with things like mass and length. Okay, and that's the general or special theory of relativity we'll talk about. Okay, so key information, light is fast. How long would it take light to reach the Earth from the sun? Well, if we use the orbital radius of Earth, 1.5 times 10 to the 8th, that's how many kilometers we are from the sun. We could calculate that, right? If we just take the distance and divide it by the velocity, we get the time. Now notice I converted the kilometers, right, into meters here because our speed of light is in meters per second. Okay, so that's why it's 10 to the 11th down here. So if we go ahead and do that, we see it's about 500 seconds or just about 8 minutes. Okay, so for all we know, the sun could have burned out, but it'll take us 8 minutes before the lights go out here. Now we know our sun is going to burn for quite a while here. Certainly many human lifetimes, so nothing we need to worry about in our age or for at least our descendants here for a while. All right, let's talk about the electromagnetic wave spectrum. So the light we've been talking about so far is what we call visible light, okay? So visible light is what we can detect, the human eye has evolved to be able to detect. And it's made up of this color spectrum. Now, you guys have seen this before in your previous classes, right? And this is actually a fairly narrow frequency range or fairly narrow set of wavelengths that we can detect as visible light. The electromagnetic spectrum itself is extremely wide in terms of frequency and wavelengths, okay? And we'll look at the full spectrum here. But the visible spectrum, right, is made up of, we sometimes say, the colors of the rainbow, right? And you might remember this from your early science classes, Roy G. Biv, right? How do we remember those colors? So red, orange, yellow, green, blue, we call it indigo, kind of a dark blue, and then violet, okay? Now, excuse me. Now, those aren't the just 7 colors that make up the spectrum. Obviously, there's an infinite variety of shades as we transition from one color to the next there, as we go from one wavelength to the next. So visible light, very small part of the spectrum. The wavelength of visible light is on about the same size as a single-celled organism, so like a bacteria or an amoeba, right? So they're fairly small wavelengths here. Now, if we go to a longer wavelength, the next part of the spectrum to the left or below visible light is what we call infrared light. Now, infrared basically is associated with heat. When an object is warmer than just about absolute zero, it will give off infrared radiation or infrared electromagnetic waves. And the warmer it is, the more infrared energy is given off, right? Sometimes we use infrared cameras to be able to detect heat sources. You know, if they're searching for a person in the woods or something who's lost, they'll use infrared camera because they can see the heat of their body easily. The size of the infrared wavelength is about the size of the eye of a needle, okay? So a little bit longer. The next are microwaves. So this is the exact same microwave that's used in your microwave oven to warm up things. As long as there's some water content in there, it will warm up. But microwave waves are also used for communications. Our cell phones tend to transmit at kind of low microwave frequencies. And the wavelength of a microwave is kind of on the size of maybe an ant, right? So a few millimeters long, or maybe even a fraction of a centimeter, okay? The next waves are radio waves, right? So these get lower in frequency and longer in wavelength. So as we move to the left here, what I want you to think about is long wavelengths and low frequency. The lowest radio waves, like we'll use on our AM radio in the car, those frequencies are on the order of, say, a few hundred kilohertz. You know, 680 on your station, if you're a Giants fan, right, is 680 kilohertz. That's the frequency that AM radio is using of the spectrum. The wavelengths are very long. It's 10 to the third. That's about 1,000 meters or a kilometer long. So one full cycle, you can't see it in the air, but one full cycle of an electromagnetic wave would be a kilometer long, okay? So very long wavelengths, very low frequencies. If we go the other direction, right, we get ultraviolet. So ultraviolet gets higher in frequency, shorter in wavelength, And ultraviolets, as we mentioned earlier, can be very dangerous to most life on Earth. Fortunately, right, we have our ozone layer that filters out most of the ultraviolet radiation for Earth. Some of it gets through, but this can cause damage to just about any type of living tissue if it has too much for too long a period of time. The wavelength here is, say, on the order of a virus, right? So the coronavirus that we're dealing with right now, the size of that virus is about the length of a ultraviolet wave. Now, ultraviolet, because it does do damage to living organisms, actually makes a really good sterilizer. So they're using ultraviolet light to actually sterilize things like masks and protective equipment in rooms and hospitals. It will kill off the virus. Then we get up into X-rays, very high frequency, very short wavelengths, right? These are produced and used, say, for imaging, right? If you go and get an X-ray at the hospital, it's using electromagnetic waves that are at this very, very short wavelength. So the wavelength is now getting down to the level of the atomic structure. And then the highest part of our spectrum is what we call a gamma ray. And these things are extremely high frequency, very, very short wavelengths. Can be somewhat difficult to detect in nature. They have these big detectors they built down under the earth to try and measure gamma ray radiation. But the wavelengths here are below the atomic structure level. So these are kind of subatomic, extremely small. Okay, so as we go to the right, we have very short wavelengths and high frequency. As we go to the left, we have very long wavelengths and low frequency. The key is that every one of these waves, though, is the same. It's an electromagnetic wave. It has those two components that move through a vacuum or through any media. And it's just the very narrow frequency range that we call visible light that we can detect. All right, the last thing in terms of fundamental light before we get on to color here is, does the wave equation apply to light? And it certainly does, right? Velocity equals wavelength times frequency. So let's look at a couple of simple examples here. Let's say we want to find the wavelength of red light in a vacuum. Now I should qualify, right? That speed of light that I gave you before, 3 times 10 to the 8th meters per second, is the speed of light in a vacuum. Light does slow down. It won't get any faster than that, but it does slow down if it travels through certain media. And we'll get into that in future lessons. But in a vacuum, we'll use 3 times 10 to the 8th. And red light has this frequency of 4 times 10 to the 14th hertz. So if we were to plug that into our wave equation, solving for the wavelength, we're just going to divide the speed by the frequency. And we get this as our wavelength, 7.5 times 10 to the negative 7 meters, right? Extremely short wavelength, less than a millionth of a meter in length. How about if we want to find the frequency of violet light? Well, same thing. We're just going to solve for frequency now, though. So velocity divided by wavelength, and we get the frequency 7.9 times 10 to the 14th hertz. Okay, so we can use the wave equation for light as well. The velocity, as long as in a vacuum, will always be 3 times 10 to the 8th meters per second. All right, let's shift gears and talk about color. So as we know, visible light is made up of all the different colors, and we can actually see that if we take, say, sunlight, right, that has a full spectrum of light in it, sometimes known as white light, and we have that shine through a prism. The prism is going to bend or change the direction of the light depending on the frequency. So as it does that, it's going to separate out the colors. Now, if we were in class, right, I give you guys a prism, you go out on a nice sunny day, shine the light through it, and be able to see the different color spectrums here that the prism would separate the white light into. So the key thing is white light is made up of all the colors. And if we put an object under white light, it appears white because it has all of the colors together. And if we take all the colors and run them back through a prism, they will combine to form white light, right? So this process is reversible. It works either way. All right, let's first talk about color by addition. So we're going to introduce some names here for certain sets of colors. And the first is what we're going to call primary colors. And the primary colors are red, green, and blue. Okay, so why do we call these primary? Because virtually every other color can be formed by mixing red, green, and blue. Okay, so we call this creating color by addition of light. We can add different amounts of red, green, and blue to produce different lights, different other colors rather. So this little wheel here is something we're going to use a lot, right? So it starts with our red, green, and blue, but what happens if we add them? And that's shown here by where the circles overlap, okay? Now, if we just have red and green, when that mixes, we get yellow. Right? If we just have red and blue, that mixes, we get magenta. That's the color we're going to give to adding equal amounts of red and blue. If we mix just green and blue together, we get, sometimes we call this turquoise. The physics word we're going to use is cyan, C-Y-A-N. Okay. Now, if we mix all three, red, green, and blue, then we get white, right? Because white is the presence of all of these colors. Now, the three different colors that we got by mixing the primary colors, we call those the secondary colors, okay? Magenta, cyan, and yellow are considered secondary colors that form when we combine any two of the primary colors. Okay, so we call this creating color by addition of light. Now, most of us, I think, can relate to this, right? If we have two different colored lamps and we shine them together, we kind of see what the result is when those colors mix or add together. So let's look at an example. If we're in a darkened room and we have two colored spotlights, one red and blue, and they shine onto a white screen, what color will appear where the two lights overlap? Well, we have to look at our little overlapping color circles, right? What are red and blue going to produce? Well, if you look at the wheel or look at your notes, right, they're going to give us this color called magenta. Okay, so an example of color addition. Let's look at one more. What would we get in a darkened room? So when I say darkness, we can assume there's no other light sources. The only light source we're going to have are these two colors. So in this case, blue and green are going to shine onto a white screen. What color will it appear when they overlap? Well, green and blue gives us cyan. Okay, so color by addition is pretty simple, right? We can just look at our wheel and say what happens when we combine any of these colors. The other method we're going to look at, and this is kind of the last part to our lesson today, is color by subtraction. So let's go through an example here of what we mean by subtraction. So we have a darkened room. We have three colored spotlights, right? Red, green, and blue. So we have all of our primary colors shining onto a sheet of paper. The paper is going to absorb yellow. So what colors are being absorbed by the paper? Well, what is yellow made up of, right? Yellow is made up of red and green. Oh, I'm sorry, it doesn't absorb yellow, it appears yellow. Let me back up, okay? So the paper is gonna appear yellow. So yellow is made up of red and green, but yellow doesn't have blue in it. So therefore, which of the three colors will the paper have to absorb so that it will appear yellow? Well, we know it's going to have to reflect red and green. That will give us yellow, but we don't want it to mix the blue in with the red and green, so it has to absorb the blue, okay? So the paper is going to reflect red and green to produce yellow, and then it absorbs the blue. So what is the paper doing, right? There's something in the paper that's causing it to subtract the blue out of the light and just leave us with red and green. So this is what we mean by color by subtraction, right? We're absorbing or removing a certain color from the light that's shining on it. And then whatever colors are left over, that's what we will see. So colors by reflection, right? Or subtraction, it's really the same process. It depends on a couple factors here. The first is what is the color or wavelength of the light that's shining on the object, okay? So that's the first thing. What color light do we have? The second is what color or wavelengths are going to be absorbed by the object, okay? So back to that piece of paper, there was something on it that would absorb blue, okay? And then the other part of that is it absorbs certain colors. The rest are the colors that will be reflected. Okay, so three things. What color is the light shining on it? What colors are going to be absorbed? What colors are going to be reflected? Okay, so let's look at some examples. If we have white light shining on white paper that's going to reflect all colors, what will it look like? Well, since white shines on white and white reflects all the colors, we're simply going to see white. Okay. Now, what if we shine a blue light on a white that's going to reflect all colors? It's going to appear blue, right? Because the blue will get reflected. Same thing with yellow, right? Same thing with green. Any of the colors, if we shine it on a white piece of paper that absorbs no colors and reflects all colors, will basically be whatever the color of the light is. If we shine light on a black paper, oh, I guess I got one more. Okay, if we shine light on a black paper and assume that black absorbs all light or all colors, now has to be really a special surface of black to completely absorb all light. If we have like on a black sweatshirt, right, we can see it's black, but we can still see some of the features of the sweatshirt, right, the stitching or the texture of the fabric. So you know that it's reflecting some light, not absorbing all of it, but it's reabsorbing most of it. Okay, so if we shine a white light onto a black paper, it appears black. Okay, or for that matter, any color that we shine on to black paper should absorb most of that color. Now, what is it that actually absorbs those colors? They are called pigments. Okay, pigments, or think of them as certain dyes that absorb some colors and reflect others. So when we have color by reflection or subtraction, it's actually the pigment in that material that's doing the subtracting or absorbing. So if we shine a white light on a red object, the pigment is going to have to absorb green and blue, right? Because if we shine all the colors onto it, but we want it to appear red, the job of the pigment is going to be absorb the green and blue. So it's subtracting that, and all that's left is the red. So it's going to reflect the red and make the paper appear red. Okay. So red paper has a pigment in it that absorbs green and blue and then reflects the red. Okay. What if we put blue light on a red paper? What's the pigment going to do? Well, we know from the example on the left, it's going to absorb the blue light. Right? Is there going to be any color to reflect? If all we're shining is blue light on the paper, it's going to absorb the blue and not reflect anything else. So what would that spotlight look on it? Basically, it would appear black on the paper. Okay, so if you shine a blue light onto a red piece of paper, it's going to appear black. Okay, and again, if we were in the classroom, we could do this and have some fun with it. But if you've got any colored lights at home, you could certainly give this a try. All right, so let's get this into our notes. This is important. We're going to talk about what are the primary pigments. And primary pigments are those that absorb one primary color. So there are three primary pigments: yellow, cyan, and magenta. So yellow, think about it. If you want yellow, if you want it to appear yellow, think of our color circles here. That means we want it to reflect green and red, but absorb blue. Okay, how about cyan? Well, cyan is made up of green and blue, therefore we want it to absorb red. Magenta is made up of red and blue. We want it therefore to absorb green. Okay, so the names of the pigments are the secondary colors, but we call them primary pigments because they absorb one primary color. Okay, that's where their name comes from, because clearly the names we give them, yellow, cyan, and magenta, are actually the secondary colors that form, right, when what gets reflected combines, right? If we absorb blue, we're left with red and green, which forms yellow. We have another set of pigments called secondary pigments. And they call them secondary because they absorb two primary colors, okay? So if we want something to appear red, it has to absorb green and blue, right? So a red pigment is going to absorb green and blue. A green pigment would absorb red and blue, and a blue pigment would absorb red and green. Okay, so Secondary pigments absorb two primary colors. Okay. And if you want to think about it, secondary, right, would give us yellow, cyan, and magenta. If you think about the colors that it's going to absorb, right, this first one would be green and blue would be cyan, red and blue would be magenta, and red and green would be yellow. So it's going to absorb cyan, magenta, and yellow and leave us with red, green, and blue. Okay, so let's look at some examples to see how this works. Transmission. If you have light shining, say, through a piece of glass, what colors are going to shine through? Well, let's assume it's sunlight, so we have all the colors shining through a piece of glass, but let's say we want that glass to appear blue. So sometimes think of stained glass windows in churches and things like that, right? They have pigments they put on those glass to absorb certain colors and let other colors be transmitted through. So if you wanted the glass to appear blue, that means we want the blue light to come through and the other colors we want to have absorbed, right? So what kind of pigment would we put in that glass? Well, if we wanted to absorb all the other colors, we would need a pigment that would absorb red and green, but let blue come through. Oops. Common window glass, right, doesn't have any pigments in it, and it lets all colors pass equally well. So we see nice, good colors through clear window glass, right? All the colors come through. All right, let's look at a couple final problems here that'll help you with the assignment I'm giving today. Hopefully you've got this little pigment chart in your notes here, but we're going to use that. It's going to be handy. So we want to name the primary pigment, right? That must be on the paper, and we're going to figure that out based on what's happening with the light that's shining on it and the light that's reflecting and the light that's absorbed. Okay. So two different lights are directed towards a sheet of unknown paper. So this paper is the same, okay? Has the same pigments. So we were trying to figure out what pigments are in the paper. So the one on the left, right, we're shining a blue light on it, and it shows blue. So we know that since it's reflecting blue, it can't contain yellow pigment, because the yellow pigment would do what? It would absorb the blue. So we can't say for sure does it have cyan or magenta with just the one on the left, but we can say for sure that it can't have yellow, right? Otherwise we wouldn't get the blue light being reflected. How about the one on the right? I have this little video window here. I'm just going to close this. So hopefully that doesn't get in your way on the screen. So we have yellow light shining on the paper. Well, we know yellow is made up of red and green. So the paper appears green, which means it's going to reflect the green and it's going to absorb the red. Now, if it's reflecting green, that means it can't have magenta pigment in it, right? Because magenta would absorb the green, and yet we're seeing the green light reflected. So we can cross out magenta. It's not going to have magenta. Now, what color is being absorbed? Since we have yellow light, right, that's made of red and green, that absorbs the green, reflects the green, therefore it has to absorb the red. And that means it must have cyan as our pigment in it. So both these papers have cyan, they're going to absorb red. The one on the left with blue light, it's kind of a don't care, right? There's no red light present to absorb, but it will reflect the blue. The one on the right, it had red and green light present in the yellow, reflects the green and absorbs the red. All right, let's try one more like this. Same problem. I'm just going to pause here for a second, see if you can figure out what pigments would be in either of these pieces of paper. Okay, so let's go through the same process. We have cyan shining on the paper on the left. Cyan is made up of blue and green. Now, what color does the paper reflect? We can see it's reflecting green, which means if it reflects green, it cannot have magenta, right? So let's cross off magenta here. But it is reflecting but it is absorbing the blue, right? Cyan had both blue and green, it reflects the green and absorbs the blue. Therefore, it has to have yellow pigment in it. How about the one on the right here? Well, we have yellow light, which is made up of red and green. Okay, it appears green, which means the red is being absorbed. And if the red's absorbed, it means we must have cyan as our pigment. Okay, and then we already know that from the example on the left, that it is not going to have magenta because it needs to reflect the green. In both cases, right, is reflecting the green. So no magenta pigment. Okay, so there's an example. The assignment you'll have that goes with this lesson will have you do a number of these kind of problems trying to determine either what the pigment is, or if I give you the pigment, right, what will be the light color that gets reflected off of that surface. Oh, I do have one more. Okay, yellow light is shining on a shirt containing cyan pigment. What color will the shirt appear? Well, if it has cyan pigment, that means it's going to absorb red. What color is yellow made up of? Red and green. So if it absorbs the red, it's going to reflect green. So the shirt would appear green if we shined a yellow light on it. The last thing on this, I'm going to put these links here for a couple other YouTube videos in the Google Classroom. And take a look at a few of these. The first one is just how do humans perceive color. It's a great short, well, these are all short videos, just a few minutes long. So it talks about physiologically what goes on in our eye, what goes on in our brain in terms of how we perceive colors. The second one is kind of a fun optical illusion you can do hopefully on your device. I think a bigger screen like a tablet or a laptop works best. The third one is about a gentleman who has total color blindness, right? So everything he sees is grayscale, okay, just like a black and white TV. But what they've done is implant a device in the back of his head that transmits certain audible frequencies, so certain sound frequencies to his brain based on the color that the camera is picking up, right? So he's able to actually hear colors, very interesting. And then the last one kind of touches on color blindness again. Color blindness is fairly common in men, not so common in women, but many men, a fairly significant portion of the population of men have color blindness. And this is a fun little video that likes you to kind of see, do you have any color blindness by seeing which colors you can easily detect and which colors you have difficulty detecting. So it doesn't mean there's anything wrong with you. This is a genetic thing that in particular many men find that they have. You may already be aware, right, that you have color blindness for certain colors or have trouble distinguishing certain colors. All right, so that's it, right? We know the two models for light. We understand that it's an electromagnetic wave and what the spectrum is made up of. We can apply the wave equation using the speed of light. That's a constant in a vacuum. And we know how we can create colors by both addition and subtraction with pigments. All right, thanks. That's it for today.